Your socks aren't attracted to each other. Something far stranger is happening. We've all felt it. You pull a load of laundry from the dryer and find your shirt wrapped around a pair of pants like they're old friends. Clinging. Inseparable. Most of us assume there's some kind of magnetic pull at work, that the fabrics are attracted to each other. But that's not what's happening at all. The real story is about invisible particles, transferred energy, and a phenomenon that wasn't fully understood until the 20th century. Let's go back to 1740. A Scottish physician named Charles François du Fay was experimenting with amber and feathers in his laboratory. He'd rub amber with fur, then bring it near a feather. The feather would jump toward the amber. He assumed magnetism, but then something puzzled him. After the feather touched the amber, it would suddenly repel, fly away. Magnetism didn't work that way. Something else was at play. Du Fay ran dozens of experiments. He rubbed glass with silk, amber with wool. Each time the pattern repeated, attraction then repulsion. He proposed something radical. There weren't one but two types of electrical charges. He called them vitreous and resinous. One repelled its own kind but attracted the other. He didn't know it yet, but he discovered the foundation of all electrical science. Fast forward 200 years. Scientists renamed Du Fay's charges positive and negative. They understood that atoms themselves contain these charges, protons positive and electrons negative. But here's what most people still don't know. Electrons are loose. They move, they transfer. And when fabric tumbles in a dryer, they're constantly jumping from one surface to another. This is where static cling actually begins. Cotton and synthetic fibers have different affinities for electrons. Polyester, nylon, acrylic, these synthetic materials are electron hogs. They grab electrons easily. Cotton and wool, they give electrons up more readily. So in your dryer, as fabrics rub together, electrons flow from cotton to polyester. One piece becomes positively charged. The other becomes negative. Now both pieces have an electrical charge. Opposite charges attract, remember Du Fay's feather? But here's the twist. They're not magnetically attracted. They're electrostatically attracted. The negatively charged sock and positively charged shirt create an invisible electromagnetic field between them. That field is strong enough to hold fabric against fabric until you peel them apart. But wait, there's a second mechanism at work, and this one's even more subtle. When you rub two surfaces together in a dry environment, you're not just transferring electrons. You're creating a triboelectric effect, a fancy term for what happens when certain materials touch and separate repeatedly. The friction itself generates charge. It's not just that electrons move. The rubbing action creates the separation. This is why static cling is worse in winter. Cold air is dry. Moisture in the air normally dissipates electrical charge. It conducts electricity, carrying the charge away harmlessly. But in a heated winter home, humidity drops, the air becomes an insulator. Charges build up on fabric and have nowhere to go. They stay put. The attraction intensifies. Summer, humidity is your friend. Water molecules in humid air act like tiny bridges, allowing electrons to leak away. Your clothes generate less charge to begin with. Static cling almost disappears. This is also why your hair gets frizzier in dry months, the same mechanism. Charge builds up on each strand and they repel each other, standing on end. So how do you actually stop it? Dryer sheets work by coating your clothes with a thin layer of waxy lubricant. This reduces friction. Less friction means fewer electrons transfer. The charge never builds up in the first place. It's not magic, it's chemistry. But there's a downside: that coating reduces absorbency over time. Towels become less absorbent. Moisture-wicking fabrics lose their edge. Wool dryer balls work differently. These spiky spheres physically separate clothes as the dryer tumbles. More separation means less friction between pieces. Less friction, less charge transfer. They're gentler on fabrics and reusable, but they're less effective than chemical sheets, especially in very dry conditions. There's also vinegar. A small amount added to your rinse cycle increases moisture in the dryer and increases air conductivity slightly. It's not as effective as other methods, but it works, and it costs almost nothing. The science is the same: reduce charge buildup by increasing humidity or reducing friction. The most effective solution: hang drying. No dryer means no friction, no tumbling, no charge generation. Your clothes won't cling because they won't be charged. But for most of us, that's impractical. We're busy, we have lives, we need our dryers. What's remarkable is how recent our understanding of this really is. Du Fay's experiments in 1740 opened the door. But the atomic model, the actual understanding of electrons and protons, didn't solidify until the early 1900s. People were doing laundry for thousands of years without knowing why their clothes stuck together. The mystery was solved only a century ago. And here's something worth sitting with. Static cling is proof that everything around us is made of particles with properties we can't see. Your clothes aren't just fabric. They're billions upon billions of atoms, each with electrons moving and transferring energy. The invisible world is constantly at work. You just feel it most when you pull warm laundry from the dryer. The next time your socks cling to your shirt, you'll know exactly what's happening. Opposite charges attracting. Electrons transferred by friction. A consequence of the very physics that holds atoms together. It's not magic. It's science. And it's been happening since the first humans ever dried fibers in the sun. Subscribe to discover the hidden physics hiding in plain sight, from your kitchen to your laundry room.